Okay, so here we are. Week 7 was last week. We just finished quiz 2. I updated this on Canvas. Week 8 is this week, February 24th. Today, Wednesday's February 26th, and then we're on spring break after we get done Wednesday. But you do have an in-class assignment on Wednesday, so please show up. And you have a pretty big homework assignment, kind of big, but it's not due until you come back from spring break. That Monday before 2 o'clock, before you come back from spring break, let me get the instructions out. What is the date? That Monday before spring break is March 10th. So Monday, March 10th before 2 o'clock. And I know some of you are going to leave it all the way to March 10th, which is fine. It's just that after Wednesday's lecture, it will be so fresh in your mind. I will give you the kind of information that will make the homework so easy for you to do that you can just get it done with and still hang on to it till Monday. But at least you got it done, and then you can refresh your memory and figure out if you were ready to hand the internet. What else? So no homework. Homework's not due next week during spring break, not till we come back on Monday the 10th. There's the PowerPoint slides, 12 through 23, a bunch of Excel spreadsheets, textbook pages, and I'll post the lecture on Canvas like usual. Here, I'll just kind of give you a glimpse of the homework. There's a written part of the homework, and here's something different you haven't seen much this semester. Matter of fact, I think it's the only second time. Here we are. We are handing in a spreadsheet this time. This spreadsheet is posted. I'm asking you to download the spreadsheet. Go in to change the name. Go File, Save As, Browse, where it will go right to where you saved it, and just change the name. Just kind of include your name in there so I know this is coming from you. You know, like we put McCarthy right here, right now, and then I would save it again, right where it's saved already. And then I'd open it up and I would do my homework on it. Hang on, cancel. Go back, go back. Now, I'm going to start with the Excel. We're learning this on Wednesday, how to do this one. But what you're doing is you're going to use the data analysis tool that we're going to have up here that we're going to talk about. We haven't used the data analysis tool yet, right? So I haven't even talked about how to install it. Is that correct? So we're going to talk about on Wednesday how to install the data analysis tool and how to use it. You're using it right here, and then you're using it again down here. You're literally going to put an analysis tool table in this blank area here, or you can put it on a separate worksheet. When I demonstrated on Wednesday, it will say separate separate worksheet, or somewhere on this worksheet, and it will ask you to tell where you want it placed. You can do whatever you want. You just got to have both of them somewhere when you hand in this homework. And then you answer the questions based on your results, based on your table that you generated from this data. This is again on Wednesday. I'm going over this in detail and demonstrating this. So that's part of your homework. I would say that's probably, it sounds hard, but once you see it demonstrated, you'll find it easy. Now this is your written part of the homework, and this is taking the same problem right there, all this data right here, and solving it twice. A, you're solving it one way, which you're about to learn today, and B, you're solving it a different way, the same exact problem. And you're going to see how the answers are slightly different from each other because of the difference in the two problems, which I'm going to talk about today. Does everybody understand what's due, though, in 2 weeks? Yeah? All right? Look at this. That's it. Two problems here on the written, and then 2 problems on the Excel. But it will take a little bit of time. You still owe me time anyway, but I don't think this will take more than an hour. All right, so now, let's get here. Quiz 3 is all about this. You're looking at quiz 3 right here. This is it. This is what's on it. Last week we talked about 2 independent samples when the population standard deviations were included in the description. This week is the other 2 equations. There's 3 equations in here. The other 2 equations are when we're given the sample standard deviation included in the problem. But then you got to look at something else now. This is what it's starting to get a little tricky. You got all the building blocks: population standard deviation, sample standard deviation, no standard deviation, no standard deviation, population standard deviation, sample standard deviation, no standard deviation. This is a different story. We'll talk about it next week when we get back from spring break. And then this is just a 1 day before the quiz that we're going to talk about this one. So we have 3 equations here, 1 here, 1 here, and 1 here. But when I say 3 equations, I mean, okay, we have, let's say we have the population standard deviation. We're gonna use the one equation here with Z. But we have the population standard deviation with Z with the p-value approach, the confidence interval approach, and the critical value approach. So you have all three of those you gotta make sure you know how to do with just the population standard deviation. Then the other two equations in this box, you gotta be able to do the p-value approach, the critical value approach, and the confidence interval approach. All three approaches here, all three approaches here. I can't remember if we're doing all three approaches here, probably not. This one's just like a mini lecture. That is quiz 3. Then we have quiz 3 on Wednesday after that population variance lecture, on Monday and Wednesday, which is in week, is it 13? Spring break, there's week 9, week 10, week 11. Quiz 3 on Wednesday. On Tuesday is the hypothesis testing for variances of two independent. That's that last box. So everybody knows what's coming up and when quiz 3 is. Quiz 3 is 15% of your grade, is that true?
Yeah.
Okay, and I'm hoping it will be more than 6 questions. I'm hoping it will be more, it's just, I don't know, the grading is awful. It is. All right, here we go. Now let's talk about the equations. Right now, we're focusing on just this first box. We're gonna review a little bit about last week's where the population standard deviations were given to us. This week is all about the sample standard deviations given to us. Here's the 3 equations. There they are. That first top one, 2 sample hypothesis testing population standard deviations given. That's that top box right there. And we learned this formula last week, and we had homework that we didn't have to hand in, but we used this equation right here. And what did I say this right-hand side on the numerator will always equal for this class? 0, and you can just do what? Ignore it, take it right out of there. You don't even need it part of the equation. All right, so there's last week's equation right there. The homework answer is already posted, so you can see examples. This week is all about these other 2 equations. Oh wait, before I go on, here's this equation to find Z, where you're given the population standard deviations, but don't forget, you gotta know the p-value approach, the critical value approach, and the confidence interval approach. Trying to remember, is there an example? Here's the confidence interval approach equation right there. This finding Z would be used for the critical value approach and the p-value approach. So finding that Z, and then if it's confidence interval approach, there it is. These formulas should look very similar to what we've been doing. The first quiz was all about confidence intervals with the same rules: population, sample, blah, blah, blah. The second quiz was all about hypothesis testing with 1 sample and a hypothesized number. Population standard deviations, sample standard deviation, no standard deviation. And this week is the same thing, but now those were the building blocks to the real research where you have 2 samples. 2 samples, population standard deviation, sample standard deviation, but here's the deal. Let me make sure you get this. This is if the population standard deviation is given. These 2 are both if it's the sample standard deviation being given. But here's the deal. This one, if the sample standard deviation is being given, but if there's a sentence that says the population standard deviations are assumed equal, that's how you know to use this formula. This one won't say the population standard deviations are assumed equal. It'll be giving you the sample standard deviations and say nothing. And that's how you know to use this one. Let me repeat that, because this is the logic behind figuring out which one of these 2 to use. I'm going to say it again. Both of these are based on you're reading a problem. There's 2 hypotheses, 2 sample means, right? 2 sample means. And they're both giving you the sample standard deviation. So you're going, okay, it's one of these 2 because we're being given the sample standard deviation. But which one of these is it? You're looking for another sentence that says, but we can assume the population standard deviations are equal. Then you know to use this equation. But if we're looking for that sentence, okay, we know now we got the sample standard deviations, and we're looking for that sentence to say the population standard deviations are equal, and we can't find it anywhere, we're going to assume they're not equal, and we know to use this equation. Everybody get that? This is the toughest part. We have 2 different equations when we are given the sample standard deviations. We've never had that before. There's always just been one equation when we're given the sample standard deviation. Now there's two of them. Let me make sure you get this. I wanna make sure you get this. So what I did is I'm gonna read this and you tell me if this is a Z last week's or this is a T from this week.
Of course.
All right, and this is two sample questions here that you're gonna see on quiz 3. According to the, let me make this bigger. Z or T, according to a health of Boston report, female residents in Boston have a higher average life expectancy as compared to male residents, okay? So one sample is gonna be life expectancy of females, one's gonna be male, it looks like. You collect the following sample data to verify the results of the report. You also use historical population standard deviations of 8.2 years for females and 8.6 years for males. And then it goes on and on and on, but you have enough information right now to tell me Z or T? Z it is, because you were given the population standard deviations, right? All right, good. And there's only one equation to use, and it was from last week's homework. You're pulling out last week's homework, look at the examples, you apply it to this question. The Chartered Financial Analyst designation, CFA, is fast becoming a requirement for serious investment professionals. It is an attractive alternative to getting an MBA, Master's of Business Administration, for students wanting a career in investments. A student of finance is curious to know if a CFA designation is more lucrative option than an MBA. She collects data from 38 recent CFAs and their mean salary is $138,000 with a standard deviation of $34,000. Then there's a sample of 80 MBAs with a resulting mean salary of $130,000 and a standard deviation of $46,000. Z or T? Why T? Because it's giving you the sample standard deviations, right? All right, hang on now, let's take this a step farther. When we have two samples, we're always checking to see if there's a difference between the two samples. We're checking to see if the two samples are equal or not equal to. We're checking to see if one sample is greater than the other sample, or we're checking to see if one sample is less than the other sample, which would make it a one-tail. My question for you is this a one-tail or a two-tail the way it read? You want me to read it again?
Yeah.
Okay, here we go. I'll stop after it's been given away. The Chartered Financial Analyst designation is fast becoming a requirement for serious investment professionals. It is an attractive alternative to getting an MBA student wanting a career in investments. A student of finance is curious to know if a CFA designation is more lucrative option than the MBA. One tail or two tail?
No.
One tail, more lucrative.
More.
The greater than would be our alternative hypothesis. Our null would be less than equal. From that sentence right there, we're trying to see if one sample is more lucrative than another sample. Is the CFA average salary, $138,000, more than the MBA's average salary of $130,000? Yes, there's an $8,000 difference there, but is that difference significant? And then the problem would go on to mention what percent significance you use to determine whether that difference is significant or not. This is a T. Let's take it a step farther. Is this a T where we're assuming the population standard deviations are equal, or is this a T where we're assuming the population standard deviations, where we're not assuming the population standard deviations are equal? Is there anything there about the population standard deviations being equal? No. So this is one we would assume that we're not assuming the population standard deviations are equal. You're about to see there's two equations. You're going to pick the one that doesn't say the population standard deviations are assumed equal, because there's nothing mentioned here about it. Let's keep going. C or T. An entrepreneur owns some land that he wishes to develop. He identifies two development options: build condominiums or build apartment buildings. Accordingly, he reviews public records and derives the following summary measurements concerning annual profitability based on a random sample of 30 of each. So 30 condos, 30 apartments of each local business venture. For the analysis, he uses historical population standard deviations of $22,500 for condos and $20,000 for apartment buildings. Z or T? Z. Because we were given the population standard deviation, so you know it's a Z. And you jump to the same formula we used in last week's homework. All right, let's keep going. David Aronson has been working as a lecturer at Michigan State University for the last 3 years. He teaches 2 large sections of introductory accounting every semester. While he uses the same lecture notes in both sections, his students in the first section outperform those in the second section. He believes that students in the first section not only tend to get higher scores, they also tend to have lower variability on scores. One tail or two tail, if I stop right there?
One.
Why?
Because it says lower.
Lower scores. He's trying to measure if one class has lower scores than the other class. That's why it's one tail right there. David decides to carry out a format test to validate his hunch regarding the differences of the average scores. In a random sample of 18 students in the first section, he computes the mean and a standard deviation of 77.4, 10.8 respectively. In the second section, a random sample of 14 students resulted in a mean of 74.1, standard deviation of 12.2. Z or T? T, because you're being given the sample standard deviations. At this point in time, hang on a minute, we already said it's a one tail, but what we didn't say, are we using the formula that assume the population variances are equal, or do not assume the population variances are equal? Do not, because nothing in there said the population variances are equal. After you're given the sample standard deviation, somewhere in the problem it will say, and the population variances are assumed equal, that's when you're going to use the first formula. Let's go back to those formulas. Unless there's one more. Is there one more? No. Let's go back. Let me get this back to the top. Let's go to those formulas again. Here are the two. Assumed equal population variances, not assumed equal population variances. But both of these have the sample standard deviations. So here we go. There's the T, first T. This is if the population's variances are assumed equal. Again, this right-hand side of the numerator is going to be 0 always for this class. You can take it right out of the formula. So you have sample 1 minus sample 2 over the square root of something brand new that's only for this formula. That symbol right there is called a pooled variance. Let me repeat that. That symbol, S with the P with the square there, that's the pooled standard deviation squared, which makes it the pooled variance. The pooled variance is only used for this formula when we're given the sample standard deviations and we're told the population variances are assumed equal. Then it's 1 over the sample size from the first sample plus 1 over the sample size from the second sample. You add those up, you multiply them by the pooled variance, you square root it, then you divide it into your numerator. You're going to see an example. I want to show you the other formula, so let me go back. This one, once you recognize that, hey, we have the sample standard deviation, so we're going to use T. And you go, oh, it says assume the population variances are equal. You now know this is the formula you use, and you now know you got to do this. Pooled variance. Let me show you the pooled variance. Oh, my little thing's in the way. Sample size 1 minus 1 times variance of 1. Standard deviation from 1 squared makes it the variance. Plus sample size 2 minus 1 times its variance for sample 2. Over sample size 1 minus 1 plus sample size 2 minus 1. Now the degrees of freedom for this formula is also different than the other formula. Let me show you the degrees of freedom. Oh, right here. If you're saying, okay, we're being given the sample standard deviation, I know this is going to be a T, you guys are all on top of it, Z or T, you go, oh, it's a T, and you're going, oh, it says population variances are assumed equal. My degrees of freedom are sample size 1 plus sample size 2 minus 2. Very different than we've had up to this point. It's the first time you've seen a degrees of freedom formula like this. Sample size 1 plus sample size 2 minus 2 for degrees of freedom. That's only for this formula, only for that category. All right, now we're going to talk about the other one to see the difference between this one and the other one. The other one is actually, the one we're about to learn, this one down at the bottom, is more common. Because in most cases, we don't know if the population standard deviations are assumed equal. And so this will be much more common, what you're about to see. So here's the difference. You ready? This T formula looks like, hang on, there. Sample 1 minus sample 2. This again on the right is always 0. You can take it right out of the formula. This is the other t formula. Look at, there's no pooled variance in this one. This one is the square root of variance of 1, standard deviation squared, over the sample size of 1, plus the variance of sample 2 over the sample size of number 2. Add those two together, then square root it, then divide it into your numerator. Very slightly different formula, no pooled variance. No 1 over either. You got the true variances over. Now, here's the big difference. All right, let me repeat where we're at. You're realizing this is a problem that uses t. And you're going, okay, this uses t, and there's nothing about the population standard deviations or variances being equal. So you know it's this formula. But here's the rough part. Degrees of freedom. You're not adding the sample size 1 and sample size 2 and minus 2 for this one. No, no, no. There's your degree of freedom formula. This is what makes this one hard. Slide 22, if anybody's taking notes. Degrees of freedom is slide 22. This is the most common T formula, this one right here, that happens to use, and this degree of freedom, because we don't see anything that says the population variances are assumed equal. So we got to use this one. Let me make sure you realize what this is saying. You ready? The variance from the first sample over the sample size from the first sample plus the variance from the second sample over the sample size of the second sample. Add those together, then square them. There's your numerator. And I got an example of this to show you. The denominator, this is the weird part, the variance from the first sample over the sample size from the first sample, but once you get that, you then square it. Then you divide it by the sample size minus 1, which is weird. Then, on the right-hand side of the denominator, variance number 2 over sample size number 2, but then you square it and divide it by sample size number 2 minus 1. Then you take each of these and add them together before you divide them into your numerator. It's not easy. It takes a little work. It's basic algebra, but the amount of time it takes you to do all these calculations. So I have to figure out if this happens to be a problem on quiz 3, do I want you to spend all your time calculating this degrees of freedom? I may give you the degrees of freedom for any T problem, so you don't know which one of these two it is, but you know it's one of these two. I might do that, and I'll remind you of that before the quiz, because I'll know by then, because I'll start writing the quiz. Okay, does everybody see what we're talking about today? What we're talking about today is that we have two formulas we're working with. Here's one of them. This is if we're given the sample standard deviations, and it says the population variances are assumed equal. There's that one, which is on slide 15. By the way, if you have to use the confidence interval approach, that's on slide 16. Confidence interval approach, if we're given the sample standard deviations, but it says assume the population standard deviations are equal, variances are equal. I say standard deviation and variances because they're the same thing. But it will most likely say variances, assume the population variances are assumed equal. There's the confidence interval. All right, and then the other formula we're learning today is right here on slide 23. This is if we're not assuming the population variances are equal, but we're being given the sample standard deviations. And there's our degrees of freedom in that case. All right, so now let's do an example up here. Okay, we're back up here. I want to refresh your memory. We just read a two-sample, independent sample problem. We realize it's a T and not a Z. We're looking at it carefully, and you also saw the sentence that says, assume the population variances are equal. You know to now use this formula right here. You now know that you add up the two samples and divide and minus 2 to get your degrees of freedom, so you can do your Excel equation. You now know you need to do a pooled variance. So here's an example of this one. Taking into consideration degrees of freedom, taking into consideration how to do the pooled variance. Here we go. You are a financial analyst at a brokerage firm. Is there a difference in the dividend yield between stocks listed on the New York Stock Exchange and the NASDAQ? Let me repeat that sentence. is there a difference in dividend yields between these two exchanges? One tail or two tail?
Two tail.
Very good. It didn't say, are the dividend yields greater in one exchange over the other? Didn't say, are the dividend yields less than in one exchange over the other? It just said, excuse me, are they different? So you know the null hypothesis is gonna be one mean minus the other mean equals 0. And the other one's gonna be one mean minus number 2 mean not equal to 0. There's your two tail. Very good. Assume both populations are approximately normal with equal variances. There's that sentence. It's telling you that assume the population variances are equal. Even though it's giving you, look at right here, sample standard deviation, sample mean. You're going, oh, it's giving us the sample standard deviation. You know it's a t. But then it says the sentence, assume the population variances are equal. Have equal variances. You now know to use that first equation. So we know the equation now. We're going to jump into it. And by the way, the significance you're going to use is 5%. Here we go. Wait, what's the mean? I got to go back to the mean. Hang on, come on. 3.27's New York Stock Exchange, 2.53. This is 3.27% yield is what it is on the New York Stock Exchange, 2.53% yield on the NASDAQ. So we subtract them. There's our numerator. The denominator, here's our pooled variance. Ready? The sample size, I gotta go back and look at the data. Sample size for the first one's 21, the second one's 25. So here we go. 21 minus 1, the standard deviation is 1.3, but we gotta square it to turn it into a variance. Plus, the sample size for the second one's 25 minus 1, and the standard deviation is 1.16, but we gotta square it to turn it into a variance. There's our numerator. Denominator, 21 minus 1 plus 25 minus 1. Look at that. That's our degrees of freedom, by the way. 21 plus 25 minus 2. So what does that equal? 46 minus 2, that's 44. Our denominator is 44, right? You do all that calculation, our pooled variance, because we're using this equation, 1.5021. So we have to plug that into our denominator. The square root of 1.5021 times 1 over the sample size, 21, plus 1 over the second sample size, 25. We do all the calculations there, we get a t of 2.040. There it is. Let's pretend we're using p-value. Go ahead.
Why was the numerator for that one 3.27 minus 2.53?
We want to subtract the means, and the means that were given in the previous slide were 3.27 and 2.53.
Okay.
So we had to subtract the means, but are you asking also about that 0?
Yeah, I was just.
You know to ignore the 0 because this will always be 0 for us.
Okay.
So you have to take that 0 right out of there because there's no use for it because it will always be 0 for us.
And then what again did you multiply to get to 1.5021?
Are you ready? It's right here. It's the sample size from the first sample minus 1 times the standard deviation that was given to us, but we had to square it to turn it into a variance. The sample standard deviation for the first sample was 1.3. The standard deviation for the second sample was 1.16, but we got to square it to turn it into a variance. 25 sample size minus 1, so there's our numerator, and then our degrees of freedom are the denominator. 21 minus 1, 25 minus 1. That's the same as saying 21 plus 25 minus 2.
I'm saying for the one above it. And above? Oh, yeah, I see. Never mind.
And then that turns into, see, and then you carry it into that, because you've got to use the pooled variance there, but here's how to calculate it.
What's the difference? When did you use that one?
This is when you know you're using t, but there's a sentence that says the population variances are assumed equal. So that's when you gotta use this. The other t equation, we're gonna go over in a minute too, but I wanna stick with this one for a minute, because I want you to see how this turns out. Now, before I show you the next slide, I want to, did I put it on here? This was yeah, and what was the degrees of freedom? 44? Here it is. I went ahead and said TIMV, I'm gonna find the critical value right here. It's 5% significance, it's a two-tail, so I'm not gonna double this. And it's 44 degrees of freedom. I added 21 plus 25 minus 2, 44 degrees of freedom. And so I get, here it is, 2.01, this equals 2.0154. Look at the number line. Plus and minus 2.0154. Our test statistic ended up being 2.04. 2.01, negative 2.01, 2.04. Our test statistics outside the two critical values. It's on the outside. Do we reject or not reject? Not all at once. We are recording. Reject or not reject? Reject. Anytime our test statistics outside the critical values, we must reject. We must reject. Okay, we got to bring it back full circle now. Let me get back to the story. We must reject. Therefore, we have evidence that there is a difference in dividend yields between the two stock exchanges. We have evidence that there is a difference in the dividend yields between the two stock exchanges. There's our sentence, our meaning, which you know is going to be on quiz 3 because it was all over quiz 2. You got to do the comparison, you got to tell me if you reject or not reject, and you got to tell me what does it mean in this story. Okay, now let's look at confidence intervals. You're going to get the same answer. We rejected here, we're going to reject with confidence interval. Oh wait, I thought it was on there. Oh, where's my notes? Where's confidence interval? Maybe I don't have it on there. By the way, I posted, I can see in my notes here that I need to tell you that I posted all of these equations. I typed this up yesterday and posted this. What you're looking at is two sample T equations. This is test statistic T, population variances are assumed equal. I put in words how to find T, the test statistic. And then here is how to calculate the test statistic. Population variances are not assumed equal. So there's both of those equations in words from the PowerPoint. Down here at the bottom are both confidence interval equations in words. And right now we have the population variances are assumed equal. So the equation we're doing right now is sample mean 1 minus sample mean 2 plus and minus the critical T square root of that pooled variance. It's going to be basically, let me show you again up here. Basically this formula right there, but we just insert the numbers is all. We get our upper and lower interval, but then since now that we're using two samples, our null hypothesis and alternative hypothesis is going to be equal to or greater than equal or less than equal to 0. So it's 0 that we're checking if it fits in the interval for these problems. Let me repeat that. Once we get the interval, we're checking if 0 fits. If 0 is within the interval, we cannot reject. If 0 is not within the interval, it's on the outside, we must reject the null hypothesis. Everybody get it? And then you relate it again back there.
Can you repeat that one more time?
You ready? We have to compare the 0 to our confidence interval, the upper and lower interval. If 0 fits between the intervals, we cannot reject. And if 0 does not fit, we must reject.
Isn't the problem behind you?
There it is. Thank you. I knew it was somewhere. Here it is. Here's the confidence interval. I knew it was somewhere. 3.27 minus 2.53, plus and minus. How long were you staring at it before you finally decided to let me know? A while? Darn. Here is our critical value. How did we get that critical value? Here we go. This is a T problem. Oh wait, we have it right here. Darn. That's right there too. Time. Here is our pooled variance, which we calculated. Let me bring up that pooled variance. There it is, 1.5021 times 1 over 21 plus 1 over 25. The whole square root comes out to 0.36278. Multiply it times the 2.0154, we get 0.731156. These two being subtracted is 0.74. You ready? The lower interval is 0.008844. The upper interval is 1.471156. Think of those two numbers. Think of those two numbers. We look at the null hypothesis, which is equal to or greater than equal to or less than equal to 0. These are all going to be zeros for this class, for this when we have two samples. So we're always comparing to see if 0 fits within the interval. My question for you is, does 0 fit in this interval, yes or no? You're right, it doesn't.
They're all greater.
So if 0 doesn't fit in this interval, what does that mean? Do we reject or not reject? Reject. If the 0 doesn't fit, we must reject. So this one's telling us we reject. Which, by the way, when we were using the critical value, it also said we reject. You know what? We might as well do p-value. We're doing p-value. We have all the information here. What's our test statistic? 2.040. Okay, let's go to our formulas. Even though I know, well, let's go to our formulas. Let's pretend we're taking the test. You're all freaked out, so you can't remember the formula. Go to our formulas real quick. We're doing t, and we're doing p-value. So here it is. What we need to remember is drop the negative symbol if it's a negative, if your t's a negative, which ours isn't, and we gotta know if it's a 1 or 2 tail right here. We were trying to see if there's a difference between the yields between the two stock exchanges, so that was 2 tail. So we're putting a 2 on the end. So this equals T, D, I, S, T. What's our test statistic? I gotta bring back the PowerPoint. You're right. It's 2.040. 2.040, comma. What's next? Degrees of freedom? I got degrees of freedom, and then 1 tail or 2 tail. Our degrees of freedom, she said, is 44. We're at this problem where we add the sample size for 1, sample size 2, minus 2. And then, is this a 1 tail or 2 tail? It's a 2 tail. We do this. Here we go. We know, you tell me right now, is this going to calculate to a number that's less than or greater than 5%? Oh, come on. Is this going to calculate to a number that's less than or greater than 5%? Before you stop it. When we did this using critical value, did we reject or not reject? We rejected. When we used confidence interval, did we reject or not reject? We rejected. The only way to reject using p-value is if our p-value is what compared to 5%? Less than. It has to be less than 5% for us to reject. If it's greater than 5%, we can't reject. So let's check. Did anybody type this in yet? Point what? Anybody type that in? Oh my gosh, you're kidding me. Oh. What are you guys, freshmen? Oh. Man. I think we're on some other planet. Equals T, D-I-S-T, 2.040? 040, comma, I can't remember, 44, comma, 2. Is this, wait, are we supposed to multiply time? No, we already said 2, didn't we? Is this, I can't see the number, 0.0473, is this greater than or less than 5%? Less than. Can we reject or not reject? Reject. There we go. We did all 3 approaches if we're assuming the population standard deviations variances are equal. But we know we're using T because we're being given the sample standard deviations in the problem. Okay, now, you ready? We're going to the next one. How are we doing on time? This is getting to be an overload. Look at this. You're now reading a problem, you're going, oh, this is a T. But there's nothing in it that's telling me the population standard deviations or population variances are equal. There's nothing telling me the population variances are equal. So I got to use the bottom equation, which, by the way, is a more common one. This is more common. And if this is homework, which you do have this on your homework, you got to show me the details how you got the degrees of freedom. You're not just adding 2 sample sizes and minus 2, you got this whole thing to do. But there's no pooled variance calculation on this one. The other one had the pooled variance calculation, this one has the degrees of freedom calculation. That's the difference between these 2 equations. This one happens to be the more common one. Here is the equation we're going to do. Once you recognize this a T, and once you recognize that it doesn't say anything about the population variances being equal, here is the equation we're going to use. So now, I put together a problem and I posted it yesterday. Right here, this is where we know this is a T, and nowhere does it say that the population variances are equal. So we know to use that bottom formula. So here it goes. This may be familiar because this is one of the things where you had to tell me Z or T. A chartered financial analyst, CFA designation, is fast becoming a requirement for serious investment professionals. It is an attractive alternative to getting an MBA for students wanting a career in investments. A student of finance is curious to know if a CFA designation is more lucrative option than an MBA. Okay, so right there you know it's one tail because she wanted to find out if it's more lucrative. She collects the data of 38 recent CFAs and got a mean salary of 138, standard deviation of 34. Boom, right there you go, oh, this is a T. We just got given the sample standard deviation. Let's check the other sample. Sample of 80 MBAs resulted in a mean of 130, standard deviation of 46. Another sample standard deviation, so you know this is a T. Now you're staring at it going, okay, is this telling me the population variances are equal at somewhere? At 10% significance level, is a CFA designation more lucrative than MBA? Says nothing about the population variances being assumed equal. Nothing about it. This is how you know to use the second formula, the bottom one. It's because it doesn't say anything about it. So first, here are the hypotheses. Mean 1 minus mean 2 is less than or equal to 0. Mean 1 minus mean 2 is greater than 0 is our alternative hypothesis. Yes, the left-hand side for these two samples are going to be either mean 1 minus mean 2, or it's going to be proportion 1 minus proportion 2. But this is your left-hand side of every hypothesis for this third quiz. Mean 1 minus mean 2, or proportion 1 minus proportion 2. All right? And 0 is always your right-hand side for this third quiz. So you know the hypothesis will always be 0. Now I'm going to start with the p-value approach. Look at my degrees of freedom. Wait, it keeps going. Hang on. Look at this. I made the mistake of picking a problem that has huge numbers. 138,000, 34,000, 46,000. Look how big these numbers are. I'm just going to point out, here's the equation. Here's the equation. You take the, where is it? The standard deviation of the first sample, 34,000, you got to square it, turn it into a variance. Divided by the sample size, 38. The second sample's standard deviation of 46,000, you got to square it, turn it into a variance, divided by its sample size, 80. Once you do all of that, you got to square it for the numerator. My numerator comes all the way down, turns into, look at this. This is millions, this is billions, this is trillions. What's after trillion? 3 blankety blank after trillion. 234 trillion, 316 billion, 627 million, 244,000, 229.92 is your numerator. Your calculators may not go this far, but the computer calculator will, just so you know. Windows or Apple's calculator that's on your computer will go this far. Your denominator ends up being, again, here's this, thousands, millions, billions, trillion, 33 trillion, 867 billion, 631 million, 716,134.506. You divide that in, you get 95.5. Now here's the deal. I want to make sure you get this. The degrees of freedom have to be the integer portion of the result. I'm going to put it in better words. Round down, period. No matter how big the number is, round down. That's the integer portion of the number. I'll put it in my words, round down. Can you believe it? 95.5, you want to round to 96, but that's not how it is for degrees of freedom for this formula. You got to use just the integer part of the number according to the instructions, your book, your PowerPoint, and I change it to round it down. 95 ends up being the degrees of freedom. Look at all that work just to get the degrees of freedom. And you're using the degrees of freedom here, if you're finding the p-value, and here when you're finding the critical value. You did all that for those two Excel equations. So that's what this is for. All right, let me keep going with p-value. We're wrapping it up. How are we doing on time? When you pack up, it scares me. All right, here we go. 95 is my degrees of freedom. So now I'm saying, okay, let's get our test statistic. Sample 1 minus sample 2, 138 minus 130, over the square root. The variance from 1, 34,000 squared over the sample size, 38, plus 46,000 squared. We got to turn the standard deviation to a variance. Divided by 80, there's our denominator. We do all this, there's your test statistic, 1.06. Now I'm going to use that test statistic, and this is T. I'm going to use that test statistic in my p-value Excel equation. Equals T, DIST, 1.06, degrees of freedom, 95. that whole math to get that 95, just so we can plug it into this Excel equation to get our p-value. Comma 1. Our p-value 0.1459. What was our significance we were using in the problem? I gotta go up and look. 10%. 10%. So look at our p-value 0.1459. Do we reject or not reject? Very good, because you caught your, okay, I knew you'd get that. Not reject because our p-value is larger than our significance. 14.5% is greater than 10%, so we can't reject. And that's where I'm going to stop today. From here, I want to show you critical value approach, confidence interval approach. And that will get you through the written part of your homework. And then Wednesday, we're also going to get into Excel, generating those tables to do the Excel portion. Anybody who hasn't signed in, make sure to sign in. If you walked in late, didn't get your quiz, there's 4 people, your quiz is up here. Come and get it.
I know.